So this theorem is officially the test for spanning. Actually, let's just write that down. Test for spanning. This really just gives you a way to determine, if you have our list of vectors, how do you determine whether they actually are enough to generate Rn? So here's how you can tell. So the vectors, I'm going to write it out completely so that really you can just refer back to this piece entirely. You don't have to trace back through all the work we did. So the vectors in this list, x1, so I'll write it out as coordinates x11, x21, down to xn1, x2, which are x12, x22, down to x2n. So this list of vectors spans Rn when, that's what we're going to say here. So this list of vectors forms a spanning set for Rn if and only if, so this is a necessary and sufficient criteria for these vectors to form a spanning set for Rn, and here's what it is. If the matrix, which we can write down, you don't have to call it A if you don't want to, but it's just a habit, I guess. If this matrix, just in other words, just take these columns and paste them together into this matrix and check if that matrix is invertible. So x11, x21, all the way up to xn1 is the first column, x12, x22, down to xn2 is the second column, and then you just follow the same pattern up to your very last column will be x1n, x2n, all the way down to xnn. If and only if this matrix is invertible. And that is your test for spanning. Okay, so that took quite a lot of work, mostly just because of all the subscripts to keep track of, but really this contains everything now for the test for spanning. This theorem has all the information you need. If I give you a list of vectors and ask you if they span Rn, then you can just use this test to answer the question. So let's look at an example of how that might work. So this is the last example in the section. So let me just pull up the, where are they? Here it is. Okay, so determine whether these vectors, and they're actually, I'm going to call them something different just to show you how the naming doesn't matter. So the vectors are as follows. V1 is 1, 1, 2. V2 is 1, 0, 1. And V3 is 2, 1, 3. So determine whether these vectors span or generate R3. That's what we're asked. So how are we going to do that? Well, the solution, we're just going to use the test for spanning. We've got our vectors, right? There are three-dimensional vectors. We know what their coordinates are, so we can just form this matrix, but from these vectors, and then check whether it's invertible or not. So the solution will look like this. We'll set A to be, well, it's going to be a 3 by 3 matrix because we want to know these are three-dimensional vectors and we want to know when they span whether they span R3. So we've got a list of 3 vectors and they're all three-dimensional. So that's exactly the situation that this test applies to. So we'll write the first vector as the first column of A, 1, 1, 2. Now our second vector will go 1, 0, 1, and then 2, 1, 3 will be our last vector as the third column. Let's check if this matrix is invertible. Let's take its determinant. The determinant of A, I'm just going to do cofactor expansion along the first row here. You can do cofactor expansion along the second row if you want to take advantage of that 0, but to be honest, it's just a habit to me. I like to do it on the first row whenever possible, and it's not that much harder. So I'll have 1 times the determinant of 0, 1, 1, 3. Then we'll have minus 1 times the determinant of 1, 1, 2, 3 as our second determinant, and then plus 2 times the determinant of 1, 0, 2, 1. But that's what you get for cofactor expansion. And what you're going to get from that is, well, this will be 1 times this determinant, which is going to be 0 minus 1. So you'll have 1 times negative 1. And then the next term will be minus 1 times the determinant of this 2 by 2 matrix, which is going to be 3 minus 2, which is 1. And then your last term is going to be plus 2 times this determinant, which is 1 minus 0, which is 1. So you get negative 1 minus 1, which is minus 2, plus 2, which gives you 0. So therefore the determinant of A, this 3 by 3 matrix, is actually 0. So this matrix is not invertible. So therefore, we can answer the question. R3 is not equal to the span of V1, V2, V3. So that's how this test works. So the answer is no. These vectors do not span R3, and this is just the most brief way to state that. One thing you might notice is these vectors were written in tuple form or ordered triple form, and we actually had to turn them into vertical columns to actually apply this test up here. But what would have happened if I had just used them as rows instead? Well, in this example, you actually notice I would have got the exact same matrix. And that is a bit of a fluke in this situation, right? It's just the way these coordinates worked out that it doesn't matter if you put them as rows or columns, you end up with the same matrix. So in this case, if we had just used these as rows instead, we would have got the exact same result. But actually, even if that weren't the case, we could also have just put these together as rows. Because remember, a matrix is invertible exactly when its transpose is invertible. The determinant of a matrix A and the determinant of its transpose are going to be the same thing. So you could also adapt the test for spanning and just use these as the rows of your matrix A, and you wouldn't change anything. That wouldn't harm anything at all. So you can just use your own judgment. Which would you prefer to do? Do you want to set these up as the rows of your matrix, or do you want to set them up as your columns? There's no harm in doing either or. So that's the test for spanning. Yes, the important thing I know there was a lot of indices and theory here. This is the important part of this second, the last few parts of section 4.2. Everything for the test for spanning is in this theorem, and the idea of applying it is in this example. So this is the important part. Everything you see on the screen right now is what you really need to take forward from this section, or from the last half of this section. Okay, that completes section 4.2.